Okay, so this is the first video of section 5.4. In this section, I'm going to introduce several more complex models that are produced from very basic percolation and growth models. Okay, the first type of models I want to introduce here, they are called neutral landscape models. They are based on percolation models. So what are these? You can consider them as null landscapes for comparison with actual landscapes. So landscapes, they are formed by different land cover types, right? And these null models, they can be considered as a baseline. They're ideal, they're simple. That's the reason why they are baseline. They're baseline. You can compare the real landscapes with them. Here on the right side, we have two null landscapes. The first one is called simple random. So we can consider white cells as occupied cells, black cells as unoccupied ones. They're randomly distributed within space. But at the bottom, we have this hierarchical random landscape. Obviously, we have some pure white patches here within the space. So this is actually a two-level model or two-level null landscape. The first level of this landscape divides the whole space into two types, type A and type B. Let's just say type A is for all those patches, or you can say all those pure white patches, they are type A. And the background sites, no matter occupied, unoccupied, they belong to type B. That's the first level of this model. And at the second level of this model, you can assign a specific proportion for occupied cells for type A and type B separately. Obviously, for type A within this space, all those patches, they're type A, right? And they're all pure white, which means that the proportion of occupied cells for type A is 100%. On the other hand, if we look at the background of this lattice, which is type B, all those sites, they belong to type B on the background, but some of them they're occupied, some of them they are not occupied, which means that the p-value for type B at second level is somewhere between 0 and 1, right? So 517, model 517 shows three types of neutral landscapes. First one is random, okay, is this simple random landscape. Second one, random blocky. I will show you that. You will see a lot of aggregations. They're just small blocks, small patches. And the third type is hierarchical. Okay, the whole space is subdivided at two levels. At level 1, we have type A with a proportion of P1 or PA. And we have type B, because there are only two types. If the proportion of type A is P1 or PA, the rest is 1 minus PA or 1 minus P1. Okay, so two types. And at level 2, within each type, you can also assign a specific p-value to address the proportion of occupied cells within that type. P2A, P2B, they are two p-values within type A and type B. Okay, 517. Let me show you that. 517. Okay, so here we have p-value. It is working for random. It is also working for random blocky to address the proportion of white cells or occupied cells. Okay, and for the second type, random blocky, we can also assign a specific block size value. Small blocks, large blocks, right? If you decrease the p-value, you say less blocks, because blocks are formed by occupied cells. They are white cells. If the proportion of white cells is decreasing, you should expect less blocks, right? And we also have hierarchical landscape here. And when we're talking about hierarchical landscape, p-value doesn't work. Instead of that, you have to what? You have to change p1 value to decide the proportion. Let me give you an example, right? So p1 value now here is pretty low. If we make it very large, what's the difference? What's the difference? Can you see that? It's a proportion of type A, right? Proportion of type A. If it is very small, we should say less patches. If it is very big, we should say more patches or large patches, right? So P2A is the proportion of occupied cells in type A. P2B is the proportion of occupied cells in type B. If I make it 1, what does it mean? It means that now because P1 is larger than 50%, it means that this pure white part of the lattice is actually type A. And all cells belong to type A. They are occupied cells, all of them. Why? Because P2A is 100%. Okay? Okay, that's the function of P2A. So what is the function of P2B? It controls the proportion of occupied cells in type B. If it is very low, 0, which means what? Which means that there should not be any occupied cells in type B. Okay, we have this. So you know that all those cells, all those white cells, they are type A. All those black cells, they are type B. Because in type A, all cells, they are occupied. In type B, all cells are unoccupied. Okay, so this is a very, you can say it's a very simple model. Very simple model producing different landscapes, but I didn't mention any context, specific phenomenon, or application, which means that you can use them as you want, So building block models, right? Okay, next model I want to next model based on percolation models I want to produce here. I want to introduce here is FFM. It's called forest fire model. It's considered as it is called a fire model because it can be used to again simulate forest fire, but it actually can be used anywhere, any scenario fits. Okay, it describes the dissipation of energy entering a non-equilibrium or a heterogeneous system at a constant rate, and how this leads to SOC, self-organized criticality. Actually, we talked about SOC before, but I didn't use that word. Do you still remember the critical value PSA? It's a proportion of occupied cells in OP, in ordinary percolation. Okay, when your p-value is equal to PSA or very close to PSA, your system is approaching something called critical state, edge between two qualitatively different states. Okay, so it's the boundary between ordered state and disordered state. Okay, here is an example. So here we have a platform receiving sand grains from this funnel. So sand grains, sand, or you can say sand is dripping from this funnel. So this is the initial configuration of the system, and if the sand grains continue to drip, this system is linear, is stable. The sand pile is becoming larger and larger, but nothing unexpected is going to happen so far for now. So here we have a linear ordered system. But here is the critical state of the system, or you can consider this is where when p-value arrives at p-say. So the platform here is fully occupied by the sand pile, but the sand drips, they're still dripping, and the platform cannot take more anymore. If you continue to do this, the system will just jump from linear order state to nonlinear state and disorder. And what is going to happen? We have different avalanches of sands. These avalanches could be large, could be small, could be happening anywhere on this land, on this sand pile or inside the sand pile, and you cannot predict it. Okay, there is infinite suspectibility there when your system is at this critical state. Okay, time, location, and size of avalanches is unpredictable. Cannot understand sand pile dynamics from individual avalanches. So here we have some emergent behaviors. They are avalanches, and you cannot expect them from a linear ordered system. At the beginning, nothing was unpredictable. The sand pile was going to be larger and larger until the sand pile is at this critical state. And beyond that, we have a nonlinear and chaotic system here. Okay. So what is the algorithm of FFM? Okay. Firstly, there are binary states, 0, 1, or we say tree or no tree, with user specified probability as in OP, right? Initial proportion of trees. And the fire occurs with user specified frequency, which means there could be a lot of sparks happening within a specific time, or very light sparks happening. Each spark leads to a fire, right? And any fire spreads through occupied and unburned sites. If a site is unoccupied, fire is not going to spread through it. If it is occupied, it was occupied and it's burned, then again, fire cannot spread through it. Okay, and even a site was occupied, but it was burned. But after some time, trees can grow back. Okay, this is just like the example we used in random walk model when we were talking about foraging behavior, right? We talked about the relationship between the behavior of the forager itself and the surrounding environment. And we assumed that sometimes, let's just say when on a specific site, resources have been collected by a forager. And after some time, resources can grow back, can regrow, or can respawn. This is similar. Trees can regrow at a specific rate, but much slower than the spreading of the fire. So behavior of this model, okay, it's very similar to site percolation fire model, but lattice changes spatial configuration over time because trees can regrow, right? If trees cannot regrow, a fire will spread, maybe a fire will go out, will disappear, and the spatial pattern will be just like that. Even there are more new sparks when the tree is burned. That is the final state of that cell. But since trees can regrow, the spatial configuration, the spatial pattern of trees will change continuously, which means that the spatial configuration and spatial pattern of fire will also continue to change because there are always new trees to burn. There are always new sparks, right? And also we're interested in behavior across many fire events, not just one event. This means that in this model, multiple sparks, they can happen simultaneously instead of one starting point of fire and spread. Okay, that was simple fire percolation. Okay, let me show you this model, 519. Okay, set up a specific value for spark frequency. If you make it very high, there will be a lot of fires. So make it low. Initial tree proportion, may move them, make it larger. Okay, set up. So green cells, they are for trees. Brown cells, they are for barren land, or you can say burnt land, burnt cells. And also trees can regrow on those brown cells. So can say, right? Suddenly, a huge fire burned the whole space, right? Right. And now you can see that trees are decreasing, and that's because of fire. But you can also say there are new green cells growing everywhere within the space. That's the regrowth of the tree. And on the left side and on the right side, we have two plots. Left one is the law in fire size versus law in rank of fire size, or a law in rank of fire clusters. There are large clusters with higher rank. Higher ranks, there are small fires with lower ranks. On the right side is what? Is proportion of trees by time. Okay, so this model can be run for a long time to show patterns. And you sometimes you want, when you try to draw conclusions, you need to run the same model for maybe dozens of times or even hundreds of times, and each one should be long enough. We don't have time for that, so I'll just jump to the conclusion. Here is the histogram we saw on the left side of the space, this histogram. And we also have the histogram on the right side of this model, right? Time versus tree proportions. They're very interesting, okay? Let's just jump to the conclusion. So fire size frequency distribution follows power law distribution. What does it mean? It means that, okay, large fires, they are very rare. That's the reason why the law in proportion rank of fire clusters is only -7. So there are a lot of fires, but larger ones, they are very rare. Most fires, they are small ones. Okay, so that's the first conclusion we can draw from multiple time simulations. The second one is even more interesting. Regardless of the initial proportion abundance of trees, or in other words, regardless of p-value, initial p-value, the proportion of occupied cells or the proportion of trees approaches the same value over the long term. This is something we did not expect. Same long-term behavior regardless of starting point. What does it mean? It means no matter your initial tree proportion is pretty low or pretty high, of course, 0 and 1, they are not options, okay? No matter it is very low or very high, eventually, there will be a perturbation in terms of proportion of trees. But you can see that there is variation, but still the proportion of trees is around 0.4 in long term. That is not something you cannot observe or you cannot decide from the initial state, initial configuration of the system. Okay, so this is a very interesting phenomenon and a conclusion we can draw from multiple simulations, multiple runs of FFM. Okay, so yeah, I will stop here. This is the end of the first video of section 5.4. Thank you.